Lecture 33 of Physics 72 covers the rest of the needed topics for Chapter 31. We will revisit the LRC series circuit as well as the transformers. Please take time to look at the objectives. I'll be indicating when we'll cover them along the lecture. You may pause the video if you want. 2 lectures ago, we discussed the LRC series circuit without a voltage source. Last session, we introduced the concept of alternating currents as voltage sources that may be useful for these circuits. We haven't really discussed how we quantitatively analyze these circuits in the presence of AC sources, but we did discuss a geometric way to represent waveforms, called phasors. One of our objectives today is to analyze these circuits in the presence of these voltage sources. The first part focuses on determining some equivalent resistance of the LRC series circuit that is reliant on the values for inductance as well as capacitance. The LRC circuit is in series, and our rules from DC circuits, series circuits, will still apply. This means that the same current runs through all of the circuit elements, which is why we only have one phasor for the current. Another rule is that the voltages will add up. Unlike DC circuits, voltage drops across the resistor, the inductor, and the capacitor will not be in phase, so we consider using phasors in adding these quantities. So we have to use vector algebra. Consider that the source voltage amplitude is V. Our goal is to look for some equivalent resistance, so to speak, that follows the same format as Ohm's law. Let's call this equivalent resistance R equivalent as Z. So V is equal to IZ in the same way V is equal to IR. I here is the current amplitude, or the magnitude of your phasor, and Z is called the impedance. Current amplitude is easy to get, as it's built in the function for the time varying I already. The question we must answer then is how do we get the voltage across the AC source, or VAD? And we know that whatever voltage that the source delivers is equal to the potential drop across all of the three circuit elements. Using Kirchhoff's law, we know that the source voltage will be reliant on the voltage drops across all the other circuit elements. This means the R, L, and the C. From the previous lesson, we note that these voltages are dependent on resistances or reactances, XL or XC. The inductive reactance, XL, is given by omega times L, and the capacitive reactance is given by 1 over omega C. All of these units should be in ohms. For consistency's sake, we use a cosine modulated current. We also recall that voltage across the resistor should be in phase with the current, and the voltage across the inductor should lead the voltage across the resistor by 90 degrees. For the capacitor, the voltage across the capacitor should lag the voltage across the resistor by 90 degrees. Determining the voltage delivered by the source is equal to getting the voltage drop across all of these elements by Kirchhoff's law. And lessons from trigonometry should be enough to add these elements despite having sines and cosines with them. All you need to do is to remember your sum to product identities, and you're well on your way to simplifying the sum of these expressions. Now, don't get me wrong, these are perfectly valid ways to get to the answer, but there's a possibly easier way to arrive at the result using what we've learned so far from the last time, which is phasor diagrams. If you remember, total voltage will always be out of phase from the current, but resistor voltage is always in phase with I. This only means that it's the inductor and the capacitor that contribute to the phase difference of V and I. So if you notice here, VC is pointing at quadrant 4, VL is pointing at quadrant 3, and then VR is in line with I. So really, this misalignment of V is because of these VL and VC. The phase difference will be dependent on how strong VL is compared to VC. Lucky for us, both of these vectors, or phasors, will always have a phase difference of 90 degrees relative to I, making both of them aligned to each other. Now, since VL and VC dictate phi, or the phase difference, it makes sense that we will consider cases where either XL is stronger than XC, or the other way around, to make the analysis easier. Let's work with the first case where XL is greater than XC, or that the phasor of VL is greater, or in magnitude, than the phasor in VC. With any case, we start by mapping the current phasor as well as all of the voltage phasors. So VR should be aligned to I, VL is ahead by 90 degrees, and VC is behind by 90 degrees. So there's nothing new here. We also know that IR is equal to IL, which is also equal to IC, owing to the circuit being in series. With our first case, XL is greater than XC. This means that VL is greater than VC, and that the VC vector is shorter than the VL vector. Since VL and VC phasors are aligned, we can simplify the phasor analysis by considering their difference, VL minus VC. So what we're going to do here is we're going to convert this from two vectors to one vector in the next slide. Now we could use the head to tail method in reducing our diagram by one phasor. So instead of VC being placed here, we're going to put its tail to the head of VL, similar to what we did with vector addition. With this simplification, we only have two phasors left to add, VR, the longer one, and VL minus VC. And then, applying what we know about vector algebra, we can use the parallelogram method to determine where the vector should point. So the parallelogram method entails having to form this rectangle for us to know that, okay, we're going to find some vector v that should point at the opposite end or the opposite corner from the origin. Okay. So again, true enough, our total sum or total voltage phasor should start at the origin and should end at that corner. Cleaning the rest of the component phasors, we can see that the voltage sum in red is misaligned from the current phasor in green. This confirms our earlier phasor diagram a while ago that the voltage sum is out of phase from the current. Recall that our goal is to look for some formula for the impedance Z. This should be easy enough because remember that the lengths of the phasors, V and I, are the magnitudes of the quantities that we want. From our modified Ohm's law, we have Z equals V naught over I naught. I naught, or our maximum current, is usually given with the current function. It's usually what's beside the cosine. V naught is the voltage source magnitude. And an important warning, you can see here at the bottom, our warning here is that V naught is not the algebraic sum of the maximum voltage drops. So this is already the magnitude of VL, magnitude of VC, and magnitude of VR. The idea is that V naught is not the algebraic sum of these maximum voltage drops from the inductor, capacitor, and resistor. You have to recall that the voltage drops across the circuit elements are not in phase, which is why we need to use phasors in the first place. Now, while we cannot use simple algebra to get this V naught, we can get the magnitudes of the vector sums using the Pythagorean theorem. Now, what we have to do is, instead of this equation, our equation to get V naught, because this is, okay, when you think about it, V naught is a vector, so is VL, VC, and VR. So to get this magnitude, all we need to do is apply the distance formula. Now, if you can think about it, the horizontal component, VR, so it's going to be similar to this x squared plus y squared formulation. The x component, or the horizontal component of V naught, should be VR. So we write it as such. So VR is here. And then the y component is basically VL minus VC. So we're going to write it as VL minus VC. And then we're going to square that quantity. And we're going to start with this expression for the next slide in determining how to get this VZ. Our goal is, if we know V naught, and since I naught is given to us, once we calculate V naught, we can get Z. The magnitude of the total voltage should then look like a distance formula as from the previous slide, with VR as the cosine phi component and VL minus VC as the sine phi component or the vertical component. VR was already converted to I naught R from Ohm's law, and then VL is just I naught XL here, and this is VC, I naught XC. We already have expressions for all of these, XC and XL, so we could isolate I naught because I naught is a common factor inside the argument for the square root. And it's convenient because once you divide both sides by I naught, you already get your quantity for Z, because remember that Z is equal to V naught over I naught, like so. And then from here, you should already get your final answer for the impedance. And then, okay, because we already have an expression for Z, that should already complete our first objective in calculating the impedance of a series LRC circuit. The impedance is given by this formula. The second case gives us XL less than XC, so VL is less than VC. Honestly, the mathematics is the same, and we'll end up getting the same expression for Z. The only difference is that the capacitor-inductor difference vector, or VL minus VC, will be pointing in quadrant 4, as you can see here, instead of quadrant 3, owing to the fact that VC is greater than VL. As with vector analysis, we consider getting the magnitude and the direction of vectors. So you usually get the vector direction via the angle. The magnitude of Z was already given in a previous slide. And now we determine the direction dictated by how out of phase V is from I. This is determined by the angle phi. So as you can see here. Okay. Now it turns out that since we use a formula for Z similar to how we determined magnitudes of vectors in earlier subjects using distance formula, we can also use the tangent formula to determine the phase difference. This formula is tangent phi is equal to XL minus XC over R. So if the inductive reactance is stronger than the capacitive reactance, then VL will dominate VC, and we end up with a total V that leads the current, or that your phi is positive. Conversely, if XC is greater than XL, we have VC dominating VL, and then V will lag behind the current. And in determining how to get phi, or the angle difference, we complete our second objective. So if it gets a bit confusing as how this tangent phi was obtained, remember that our Z, or the vector in mind, is equal to R squared, plus XL minus XC squared. So this is basically the Y component, which you see here, and R is your X component, which you see in the denominator. So how you got the angle phi is the same way you got the angle theta in your vector calculations back in Physics 71. This summary slide compiles what we know so far about total voltage, current, and impedance. Given a cosine modulated current, we have V is equal to capital V cosine omega t plus phi. Our modified Ohm's law gives us a relationship between max voltage V and max current I, with impedance Z as our new expression for the R equivalent. The impedance Z of our series LRC circuit is given by Z equals the square root of R squared plus the square of the difference of the reactances. Finally, the phase difference of V with respect to I is given by tangent phi is equal to XL minus XC over R. Note that the formulas for Z and phase angle are the same, regardless whether XL is greater than XC or vice versa. If XC is greater than XL, then we get a negative value for our phase angle. Let's answer a few concept items to broaden our understanding. So the first item is, which of the following is true when the source voltage leads the current? And you have 4 choices relating the inductive and capacitive reactances. If the source voltage leads the current, this can only mean that the voltage across the inductor is greater than the voltage across the capacitor. That means that XL is greater than XC, and our answer should be C. Alternately, we can look at the formula for phi, tangent phi, and see that angle phi will be positive, which leads to a voltage leading the current, if XL is greater than XC, or your argument for the numerator is positive. I'll leave this problem for you to practice by yourselves. You may pause the video if you want. The answer should be on the next slide. Getting the answers to these questions requires simple plug and play of the formulas that we have discussed so far, namely Z as well as tangent phi. So I'll guide you through this exercise. An RLC circuit with resistance equals 4 ohms, an inductive reactance equals to 8 ohms, and capacitive reactance equals to 5 ohms is driven by an AC voltage source, which we assume to be sinusoidal, with a root mean square value of 5 volts and an angular frequency of 20 radians per second. First question is, what is the impedance of the circuit? That's a simple plug and play. The second question is, what is the maximum current passing through the circuit? We're going to require a review of the RMS values for this. And finally, what is the inductance of the circuit? Which is rather easy to determine. I'll give you a few seconds. If you want to pause the video, try to solve the problem by yourselves. Now, in getting the impedance, note that XL and XC, the reactances, are already explicitly given. There's no need to multiply by omega anymore. So if we're going to calculate the value, we have Z is equal to square root of, well, R squared plus XL minus XC squared. Direct substitution gives us, this is 4 squared, and XL minus XC, that's 8 minus 5, that's just 3. That's squared. It's a Pythagorean triple, so your Z should be equal to 5 ohms. The maximum current passing through the circuit, when we determine maximum current, it should be easy. We just divide V0 by Z. The curveball thrown to us by this question is that the given voltage in the problem is in root mean square value, not really the maximum value V0. So just remember that for sinusoid AC sources, we have the following equation. So V RMS is just equal to V0 over square root of 2. This is assuming that your AC voltage source follows a sinusoid. And then the current should just be equal to I is equal to VRMS. This is your V0 multiplied by square root of 2. Then you're going to divide it by Z. And the convenient thing here is your Z is 5, your VRMS is also 5. So your current should be around square root of 2 amperes, or 1.4. Finally, the inductance of the circuit is calculated by just dividing XL by omega. Both of these are given, so that's 8 divided by 20. The answer should be around 0.4 henries. Now we move on to the last part of the lecture, which is transformers. Most transformers nowadays see its use in power plants. Recall that they change the input and the output voltage for convenience. Smaller transformers can also be seen in everyday objects, which we'll discuss in a bit. Now, from its name, transformers convert voltages. Power transmission lines usually operate at very high voltages, so it's usually VRMS equals 500 kilovolts. And it's the transformer's job to make sure that these voltages, these very high voltages delivered to households, are lowered to much safer values. These household voltages depend on the country, with the Philippines being usually at 220 volts and the United States being at 120 volts. Now, recall that transformers utilize the concepts of electromagnetic induction, so coils will be involved. Our discussion with coils last time involved vacuum conditions for simplicity, but most transformers that we use nowadays utilize magnetic materials to increase the potency of its use. The materials also confine the fields within it, which maximizes mutual inductance. Let's lay down some conventions. Primary windings are connected to where power is supplied. So in this diagram, the primary windings would be this section, and the secondary windings are connected to where you want the power to be delivered. So it's, if I'm not mistaken, it's this side. And this R here is usually a placeholder for whatever device you're trying to power up. So you can check the graphic for clarifications. The circuit diagram for transformers looks like two inductors. It makes sense because transformers usually have two coils. Now, for a qualitative rundown of how transformers work, we start with the AC source that starts an alternating current in the primary winding, as you can see here. The second one, this sets up an alternating flux in the core, because if you have an AC current running through here, then that means you should have a changing magnetic flux in this area. Okay? Because of this changing magnetic flux, it induces an EMF in both windings, not just in the primary but also in the secondary. Because the moment that the magnetic flux changes in this part, then the magnetic flux should also change for the secondary coil. And the induced EMF in the secondary winding will then drive an AC to the secondary coil itself, and eventually delivering energy to the device that you connected to. So the moment that there is an AC current that gets started in the secondary coil, this will be felt by your device. So recall equations related to induced EMFs in Faraday's law, as they will be used in determining a working equation that relates power in and power out. Note that since the magnetic field lines are contained inside the magnetic material, the flux through the first winding should be the same through the second winding, even though their surface areas may differ. And if their surface areas differ, this can lead to the magnetic field being stronger in the narrower area. So let's say one of these coils are actually smaller in surface area or cross-sectional area. Let's say this is the one that has the shorter, smaller area, and this one has the larger area. It doesn't matter because it's the same magnetic field lines that pass through as you traverse it. So to compensate, it's possible that the magnetic field lines are actually stronger here compared to here because the area here is more choked compared to the first one. Okay, from this, we can then say that they should have the same change in magnetic flux rate. And then all we need to do is we can divide epsilon 1 by epsilon 2 and eventually have a ratio of coil numbers N1 over N2. If the windings have zero resistance, so we have V1 over V2 is equal to N1 over N2. V1 and V2 indicate the terminal voltages of the primary and the secondary coils, respectively. For transformers changing voltages from power plants to households, if the voltage decreases, so will the current, using Ohm's law. This will then satisfy the inequality that the voltage and the current coming from the input of the transformer is greater than the voltage and the current that's going out of the transformer. We can then extend that to an inequality V in times I in is greater than V out times I out. Now, since the power is the product of I and V, P in is greater than P out. But for ideal transformers, they should be equal. And the only reason why they're not usually is that these inequalities will occur because of the power losses due to the resistances of the transformer. With a bit of algebra, you can then produce a similar ratio equation for current strengths and coils. This gives us N1 I1 is equal to N2 I2. Sometimes, the voltage provided by the household or industry sockets may still be too much for our everyday gadgets. The 220 volts may be a bit too much for the laptops that you use. Another process of stepping down the voltage is done via these AC adapters that come with the laptops that you buy. It's called a step-down transformer. Finally, let's try to answer one problem. Actually, it's for you to answer by yourselves. This problem is easily answered using the two equations relating voltages and currents to the number of coils. So the answers are on the next two slides. So you may pause the video to check how to get these answers. It's a simple ratio equation. And finally, To get the answer for the second question, we have this. That's it for lecture 33. Thank you for listening.